Alright, so in this video, we're going to go over section 4.1 from our textbook, which goes over the graphs of polynomial functions. So we say that a polynomial function of degree n is going to be a function of this form here. And when we say degree n, what we mean is that this variable x here, the highest power that we see is n here. Okay? And then all of these a's here are going to be real numbers, and then this a here is going to be our leading coefficient, and it cannot be equal to 0. Okay, so like I said, this a sub n here is going to be our leading coefficient. So it's the coefficient next to our variable that has the highest power. This whole term here is going to be called the dominating term or the leading term. A sub 0 is going to be our constant term. It's the only term without a variable. And because of this, if we were to plug in 0 into this function here, we would get that p of 0 is equal to just a sub 0. So that is also going to be the y-intercept of our graph of p. Okay? So the cubic function is going to be a third degree polynomial of this form here. And as we can see, it is going to be a third degree, so we have this x cubed in our leading term here. And so in general, this graph of a cubic function will look like one of these following shapes here. And on the other hand, a quartic function is a fourth degree polynomial of this form here. And as we can see, the highest power here is x to the fourth. And then the rest of our terms are written in decreasing order of the power of these variables. Okay. And then in general, the graph of a quartic function will look like one of these guys here. Right, so let's introduce some more definitions. First, we have what's called turning points. So this is where the graph of a function changes from increasing to decreasing, or vice versa. We have our local maximum point. So this is going to be the highest point on some interval. And we also have the local minimum point. So this will be the lowest point on some interval. Okay. And then we also have what's called extrema. So this is the plural of extremum. And so these maximum and minimum points are called extremum or extrema or extreme values or extreme points. So let's let C be in the domain of some function P. Then the following holds here. So P of C is going to be an absolute maximum value if P of C is greater than P of X for all X values in the domain of P. Similarly, P of C is going to be an absolute minimum if P of C is less than P of X for all X values in the domain. Now the next two are our local extrema. So P of C is going to be a local maximum if P of C is greater than P of X when X is near C. So that's where the absolute and local extrema differ. For absolute extrema, this has to occur for all X in our domain, whereas for local extrema, it's just when X is close to this value C. Okay. And the same is said for our local minimum here. P of C is going to be a local minimum if P of C is less than P of X when X is near C. Alright, so let's look at this example here. We have these two graphs, P of X and Q of X, and we want to identify and classify the local extreme points of each. So, do P of X here. Looking at this guy, we see that we have two local minimum points, AB and EH here, because if we were to, you can think of it as like zooming in on this graph. For all X values that are near this point here, this is going to be the smallest value, right? So all X values as we get super close to this point, this is going to be the smallest one. And same for this one. All X values as we get close to this point are going to be bigger than this. This is going to be the smallest value in a small region for all X values near this point. Okay. So we're looking at that would be the local minimum. So we have a local minimum point at AB and at EH. Okay. Similarly, by the same reasoning, we're going to have a local maximum point at CD here, right? So if we were to zoom in and just look at all of these X values as we get close to this point C here, this is going to be our highest point. All right, similarly for Q of X here, This JK here is going to be our local minimum. Because if we were to look at all points around J here, all of these values are going to be bigger than this point here. This is going to be our lowest point. And by the same reasoning, this is going to be our local maximum point. So we're going to have a local maximum Mn. All right. Now, if we wanted to look at the absolute maximum or the absolute extreme values of these graphs here, remember we have to look at this for all x values in the domain of P. Okay? So with that being said, let's look at P of x first here. And looking at this graph here, we see that our domain keeps going on in this direction and in this direction. Okay? So our curve keeps going on in this direction and this direction, so all of our output values keep going on in this direction. So this looks like our smallest point here, this e comma h. We're not going to see anything that's smaller than that because all of our output values, like I said, are going in this direction. So we can conclude that our absolute minimum, is going to be the point EH. Okay, so then this tells us that our absolute minimum value is the output value, which is h. That's the value we get if we were to plug e into our function. Okay? And the range for this guy, for p of x here, we know that the lowest point we're going to get is h here, and then all of our other output values are going to keep going on in this direction, so up to infinity. So this tells us that our range is h up to infinity. Now because of that, because all of our output values are going to continue on in this direction forever, we have the potential to have a bunch of different highest points here, right? We can't say for certain what the actual highest point is going to be because this is going to go on and on forever. So we'll conclude that we have no absolute maximum. All right, now let's do Q of x. Looking at this guy, this looks like our smallest value here. This was our local minimum point in part A. And so we might think that this is going to be our absolute minimum value. However, by the same reasoning, when we looked at P of x here, this graph continues on and on in this direction. So all of these values are potentially smaller than this guy. So we can't say for certain that we have an absolute minimum value. We just have this local minimum value. Now similarly, we have this local maximum point, but our graph continues on and on in this direction. All of these output values are continuing up to positive infinity here. So all of these output values could be bigger than this. We won't know for certain. So what we conclude here is that we don't have any absolute extremum for this graph here. Okay, and this is because our output value, all of our output values are going to range from negative infinity all the way up to infinity. Okay, so there's no absolute max or minimum. All right. Something to note here is that the number of turning points of the graph of a polynomial function of degree greater than or equal to 1 will be at most n minus 1. Okay, so let's look at a few examples here. If we had this linear function here, our degree is the power of this guy, and that's just 1. So n is equal to 1. So in this case, the number of turning points would be 1 minus 1. I'll make this clear. So n minus 1 would be 1 minus 1, which would be 0. So in this case, we don't have any turning points. Okay, so this concludes that we have no local extremum, right? Because the turning point, like we said, is going to be when the graph of a function changes from increasing to decreasing, and that's where we would see our extremum. Let's look at another example. If we had this polynomial function, in this case, the degree of this polynomial is 2. So n minus 1 would be 2 minus 1, which would be 1. So in this case, we would have exactly, or we would have at most, one extreme point. And lastly, if we had this cubic function here, in this case, the degree is our highest power, which is going to be 3. So this tells us we would have 2 turning points. So at most 2 extreme points. All right, so the last thing we're going to look at is in behavior of graphs of polynomial functions. So we have several cases here. We have the case when the dominating term of a polynomial function p is of odd degree. And looking at our leading term here, we have the case when the coefficient of our leading term is positive and when it's negative, and the corresponding behavior of the graphs. So if our a is positive here, then our graph is going to look like this. If it's negative, our graph will look like this. And on the other hand, if we have that a polynomial function is of even degree, with the case where the coefficient of our leading term is positive, we have a graph that looks like this, and where it's negative, we have a graph that looks like this. So we kind of breezed past these cases because the best way to illustrate them is with an example. So look at this example here. We want to match each function with its graph below. Okay. So what we'll do is just look at each of these functions and determine which case we're working with from the cases that we saw above. So for this first function here, we have degree 4, so a polynomial of even degree, and the coefficient of our leading term is just positive 1. So we're dealing with even degree, and when our coefficient of our leading term is greater than 0. So we're looking at this case here. And in this case, what's happening is as the absolute value of x goes to infinity, so does our output values. So we want to find a graph that resembles that behavior, and so it'll look somewhat like this. And so looking at the graphs here, we see that the only graph that resembles that case will be C here. And we know that that's the case because as the absolute value of x goes to infinity, so as all of these x values go to infinity, so does our output. And since we're looking at the absolute value of x, as all of these guys increase, our output goes to positive infinity. Looking at the next function here, we have an odd degree, degree 3, and the leading term, or the coefficient of our leading term, is also positive. So in this case, we have when our function has odd degree, but our a is positive. Okay. So in this case, as x goes to infinity, so does our function, and as it goes to negative infinity, so does our function. And we have a graph that looks somewhat like this. So looking at all of our graphs here, the only graph that resembles that behavior will be this graph here, B. And we know that this is the case, right? Because like we said, as x goes to positive infinity, so does our output values, and as it goes to negative infinity, so does our output values. So we know that this one's going to be B. All right. Looking at this third function here, we have degree 6, and the coefficient of our leading term is going to be negative 1. So we have even degree, and our coefficient is negative. So we're looking at this case here. And in this case, as the absolute value of x approaches infinity, our function approaches negative infinity. So we're going to have a graph that looks like this here. And looking at these graphs, a and d are the only ones remaining, and a is the only one that represents and resembles this case here. Okay. And we know that this is going to be the graph because we saw that as the absolute value of x goes to negative infinity, so as we increase all the x values over here and in this direction here, our output values are going to go to negative infinity. So this one is going to be a. Now for our last function here, it must be the case that this is the graph for this function, but we'll just make sure here. So we have degree 7, and our coefficient of our leading term is negative. So we have odd degree, and our coefficient is negative, so we're looking at this case here. And for this case here, we know that as x goes to infinity, our function is going to go to negative infinity, and as x goes to negative infinity, our function is going to go to positive infinity. So a graph that looks somewhat like this. And we see that D does in fact represent this here. We can see from this graph that as x goes to positive infinity, so increases in this direction, our output values go to negative infinity, and as x goes to negative infinity, our output values go to positive infinity. So this one is graph D. Alright, so that'll be it for this video.